Good evening, and tonight we are looking at Thermal Physics Unit 3.4. This follows really from the session 3, follows from session 1, Kinetic Theory of Gases, Unit 3.3. But tonight we'll be just focusing on thermal physics, and we'll be running through the requirements of the specification and kind of the pitfalls and going into detail everything that you need for this topic. My colleague, Mr. James Ridd from Cynfrig, a school in Bridgend, he will be doing nuclear energy and nuclear decay, session 2 and session 4. Okay, so let's start. And let's start with the idea that internal energy of a system is given by the total amount of kinetic energy and potential energy of all of the molecules in the gas. Okay, so if you've got a gas, we say that the internal energy is given by is given as U. And that is the sum total of all of the potential energies and the kinetic energies of all the molecules in the gas. And as we saw in Unit 3.3, Kinetic Theory, for an ideal gas, the potential energy will be 0, and therefore the internal energy is equal to the sum total of all of the kinetic energies. So U equals the kinetic energy, i.e. the sum total of all the kinetic energies of all of the particles. And I'll put that in terms of moles and in terms of molecules. So here, potential energy is equal to 0. Because we are assuming that there's no intermolecular forces, there's no forces between the particles at all, so there can't be any potential energy. Okay, so since what we saw from Unit 3.3, we saw that the kinetic energy of the gas itself is given by 3/2 RT for 1 mole of gas. But we could look at it in terms of kinetic energy for 1 molecule, and that can be given by, so the kinetic energy of 1 molecule, we expressed in terms of Boltzmann's constant, and we can express it as 3/2 kT for 1 molecule. And we can do that because we know that R, ideal gas constant, divided by Na, the Avogadro's number, the number of particles in 1 mole of gas, 6 times 10 to the 23, is equal to K, the Boltzmann's constant. So if we had it for 1 molecule of gas, we can jump then for n number of n number of molecules by just timesing 1 molecule by n. So we can have 3/2 n kT, where n is the number of molecules in the gas. Okay, all right. If you then have more than 1 mole of gas, we can kind of use little n, so kinetic energy for n moles, okay, is equal to 3/2 n RT, where n is the number of moles. So we've got kind of like quite a few kind of like equations in our toolbox to use. And this is true for a monatomic, true for a a monatomic gas, where the density is low and where the temperature is low. Um, Things get a little bit, so we are looking at an ideal gas. Okay, if it veers away from an ideal gas, then there will be um, factors involved, like the volume is not negligible. Um, there could be intermolecular forces. So we are going to go here, and we are assuming that the gas that we are talking about is going to be for an ideal gas. Okay, right. So that's part A. Part B is the absolute scale, or absolute zero. Absolute zero. And that is the temperature of a system when it has minimum internal energy. Now, if we are assuming it to be a ideal gas, then potential energy is already zero. So we can assume that the kinetic energy here will be zero. So i.e., at a temperature of zero on this scale, then for an ideal gas, we can say that U, the internal energy, is zero because the kinetic energy is zero. So the particles don't have any energy, they don't move at all, they've got no velocity, and therefore at T equals 0 Kelvin, the kinetic energy will be zero and the internal energy will be zero. And that happens at a temperature of minus 273.15 Kelvin, de degrees C. Okay, so naught Kelvin, that doesn't say okay, that says naught Kelvin, is at a temperature compared to the degrees C temperature scale of minus 273. You can't get a minus Kelvin. The lowest you can possibly get is naught Kelvin. You can't go below that and have a negative Kelvin. So in order to go from, say, a temperature in Kelvin to a temperature, or rather, if we want to get a temperature in Kelvin, and we've got the temperature in degrees C, then all we've got to do is add on 273.15. If you minus instead, and you end up getting a minus number for temperature in Kelvin, you know you've done it the wrong way round. So you know that you need to add on onto a temperature that's in degrees centigrade to get it into Kelvin. All right. Okay. Okay. So you can't cool it any further than from naught Kelvin. Right. So part D now. So that's part B. What have I done with part C? Is the kinetic energy. So in fact, what we've done is I've gone through this ideal gas and kinetic energy in terms of moles and molecules. This is part C. But I felt that it came in closer to A before we went on to B. So sorry for the slight change, but we can go through it and review it at the end. So moving on to part D. Now, heat enters. So if I've got a potato, okay, there's my potato, and heat enters or leaves a system at that boundary. Okay, enters or leaves a system, okay, at the boundary. Now, it depends whether the system's temperature is lower or higher than the surroundings. So if the potato is hotter than the surroundings, then the particles within that potato will be vibrating more than the particles in the surrounding. And so what happens is that energy will transfer from those hot particles in those hot potato out towards the surroundings. So it depends whether the temperature is lower or higher in order which direction that heat, that the the energy is going to flow. So we say that the energy is in transit. It's not contained in the system. Okay, so that depends on whether system's temperature is higher or lower. Okay, so what we have is, so if this is hotter, a hot potato just come out of the oven, and we say that there's energy in transit. We say that there's an energy transfer. Okay, so the hotter the potatoes, the particles are vibrating more, you've got more internal energy, you've got more kinetic energy. All right, so the molecules, because it's a solid, it's not a gas here, the molecules will be squeezed together more tightly, and so the potential energy will be greater. So a hotter potato has more internal energy. Remember, internal energy is the sum. Oh, don't know where that came from. Let's get rid of that. The sum of all of the potential energies plus the kinetic energies. So the hotter potato has more internal energy because the potential energy will increase and the kinetic energy will increase. The kinetic energy will increase because it's vibrating more vigorously, and the potential energy will increase because it's squeezed together more. And yes, I mean, the potato will expand a little bit. And okay, all right. So here, this energy here is not contained. It's not contained within the system. So there is a boundary through which energy can travel. And that change, that's why that there will be some movement of energy and there will be a change in internal energy. So whatever goes in, yeah. So if I've got a potato here, let's say, and this time we'll have 100 joules is going in. So it looks like it's a potato now that's been popped into the oven. So the surrounding is hotter than the potato itself, and there's 90 joules that leaves the potato. Okay, so the change in internal energy, that energy in transit, that transfer of energy, is whatever goes in and take away from that whatever leaves. So in this case, the change in internal energy will be 100 joules. That's what goes in. Take away 90 joules equals 10 joules. Notice it's positive. Okay, so that means that the potato is gaining energy. Okay, so let's move on to part E, thermal equilibrium. Thermal equilibrium is when a system is at the same temperature as its surroundings. Okay, and we call that the zeroth law of thermodynamics. Okay, so what happens is no heat flows. So no heat flows in or out. So no heat flows at all. So heating is the name given to the energy transfer. Name given to of the energy transfer when energy moves from a higher temperature to a lower temperature. So we can say that we are heating that potato because more energy is going in than leaving. So energy gained by heating is given by Q. And that's again measured in joules, just like the internal energy is measured in joules. So this change in internal energy is given by joules. So the internal energy here is measured in joules. I'll just pop that in. Anything in brackets I try and keep as units, so not to be confused with the quantity. Okay, right, so moving on to F. Okay, work or working. So working is a transfer of energy, usually by a force, but it could be by an electric current. So working is a transfer of energy, usually by force, where there's no movement of heat. So, for example, rubbing a potato, putting a current through a potato. And that work is given by W, and again, it's measured in joules. And we can say it's the work done in terms of the gas or an ideal gas, work done on a gas by compressing it. So, for example, if you've got a bike pump, you're doing work on that tyre by pushing gas into it, or a piston where you are compressing the air inside. And then when we say that work done by the gas as opposed to on the gas, by the gas, by expanding. So when it expands, the work is done by the gas because it's pushing outwards, whereas when you're pushing onto the gas, you are compressing it. Okay, now I'll show you how all of these link together, but let's just explore about this work first in part G. And work done is basically given as pressure times by the change in volume. So having a look at this, let's expand it a little bit and go from first principles and how we get that equation. So work done equals force times distance. But if you're looking at, say, a container and you apply a force to one of the sides so that you can compress the gas within that container, um, and you manage to compress it to by D here, the work done will be the force applied times by the distance you managed to move that through. But you know that force divided by area is equal to pressure. So rearranging that, force is equal to pressure times by area. So the area would be the area of the where you're putting the force at right angles to, normally to it. So that's the area. And the pressure is how much the force is spread out over the area. Okay, so if we take that then and we substitute for force equals pressure times area into that work done equation, so I can put that into there. So I get P, pressure, area, times by D. Now, area times by D is equal to the volume, V. So we can see that by changing it through a distance, then the change in work applied is given by P times by the change in volume. So the change in volume will be, from what you had before to what you had after. Okay, and the gas itself will have a pressure and it will have a volume. So this will change by a certain amount of volume as you push it in. And this is pretty useful because if we have a graph, say, of pressure against volume, then we can look at, and we've got a simple graph where if you apply pressure, the volume decreases. And then if we have a look at the area underneath the graph, say for a change in volume here, for that little bit, that would be the area underneath the graph. So the area underneath a pressure versus volume graph gives us the work done on that gas, W. Okay, and so that's a useful skill to have. They like producing this in an exam question. They'll give you the graph and you'll have to work out the area underneath that graph. Sometimes it's a much simpler graph. Sometimes it's just a straight line where you've got, say, constant pressure or you've got constant volume. Sometimes it's a square, but you work out the area underneath the graph. Okay, so this actually leads on nicely to point H, okay, area underneath the graph. And that is if P changes. So in the top one here, where work done equals P times the change in volume, this is when the pressure is constant. So I'll just pop that there. But when it changes, we can look at how it changes on a graph and we can work out the area underneath the graph. And there are two ways of doing this. You can either use the trapezium rule or you can count squares. So if I do it in a different color, let's do it in black. If you know the area of just one square, so you can do it, say, there's two different methods, you see. And you can count squares and then you would have to times it by the value of 1 square. And take care here, because it's likely that the pressure could be, say, times 10 to the 3 pascals, and say the volume could be, say, times 10 to the 2 meter cubed. All right, and you would have to kind of like take into account the powers of 10 to work out the value of one of the squares before you start counting them. That's one way you could do it. Anything under half a square you don't count, and anything equal to half a square or more you count as one. So you could count the number of squares underneath where that shaded area is, or you could use the trapezium method. Now, you could do an estimation of kind of like turning it into a triangle and a rectangle and adding those two areas up, or you could use the trapezium equation. Okay, so there's actually two methods with the trapezium method. You could work out the triangle, and you can add the rectangle, so area A plus area B, A plus B area. Or you could use, if you have a big area to do, you could use the equation half the distance between the intervals times by the first and last height value, because that's the thing that's changing, plus 2 times the sum of the middles. And if you're not comfortable with using that trapezium equation, stick to what you are comfortable with, measuring areas with triangles and rectangles and adding them up, or count the squares and get the value of 1 square. Okay, so that is H done. Now I. Now this is what we're all leading up to, really. The first law of thermodynamics. And there's a lot to it. And there's a lot of different situations to consider. So the first law of dynamics, let's just look at the equation. So the change in the internal energy, change in internal energy. Now, WJC mark schemes do accept this, all right? But in fact, really, because it's positive, it really should be gain in internal energy, or in the system's energy, is equal to, we ought to put of system, okay? And they like that, I noticed that. And Q is the heat added to the system from the hotter surroundings. So that's in transit from hotter surroundings, plus, or rather minus, W, the work done on the system, work done by the system, work done by the system. Okay, so we need to underline that. See how easy it is to slip into, say, work done on the system. It's very specific here in this equation. You've got to remember it as work done by the system. Okay, and I will have a few examples of the application of this particular equation. And this is where, kind of just practice with thermodynamics, and you'll click with this. Okay, so let's have a look at a couple of examples. So let's have a look at an example 1. You've got a hot mug of tea. All right, and we're vigorously stirring it. And we're doing some work on that tea by vigorously stirring it. So that's 5 joules. Okay, and 40 joules of energy escapes. Now, it escapes as conduction and convection out from the tea. So clearly the tea is going to be cooling down. So we've got the change in internal energy is given by the heat added to the system or the heat chucked out of the system. So minus W. Now, in this particular case, our 40 will be negative because it's not going into the system. It's opposite to what it says in the definition. So if the heat was added to the system, it would be plus 40. But because it's not, it's being lost. So lost energy outwards. Therefore, Q is negative here, i.e. negative 40 joules. All right, and we are doing work on the gas. It's not work done by the gas. So again, work done on the gas, on the gas means that W is equal to negative 5 joules, not positive, because it's not done by the gas. So we've got minus, minus 5. Okay, so that comes out as minus 40 plus 5 equals minus 35 joules is the change in internal energy. Okay, so can you see that it's really important language? If the energy is going outwards, then Q is negative. If the work done is on the gas, then it's a negative. And then you have to be really, really strict and kind of like obey those signs and then put them into the equation as you see it and rearrange it. Let's have another example. So let's have that we're going to increase the internal energy of a gas, of a system, of a gas, whilst compressing it. Okay, so we've got 50 joules of work being done on the gas. So we know that that is going to be negative, but loses 30 joules of heat to the surroundings. So get your formula. So change in internal energy equals Q minus W. Now 50 joules is done on the gas. So that Q will be equal to minus 50 joules. That would be slotted in. Hold on, minus 30, hold on, minus, okay. So work done is being on the gas. So W equals minus 50 joules, whilst heat is lost to the surroundings, so that would be minus 30 joules. Okay, this is because it's done on the system. The work is done on the system. And this is because, this negative here, is because you are losing, it's lost to the surroundings. Okay. Right, so let's put those in. So the change in internal energy is given by minus 30 minus minus 50. So minus 30 plus 50 equals minus plus 20 joules. So the internal energy of the gas will increase by 20 joules. Okay, let's have another example. Or shall I leave it there and keep going? No, I'll do one more example. A system has 300 joules of work done on it. There we go, that's the clue, on it. But its internal energy falls by 500 joules. Calculate Q. Okay, so change in internal energy is given by Q minus W. Let's rearrange that now so that change in internal energy plus the work done is equal to Q. All right, and that is working out the heat energy flowing. So the change in internal energy, it falls by 500, so it will be negative, i.e. it falls joules, and we're doing work on the system, so that will be minus 300 joules, so equals minus 800 joules for the heat transfer or heat energy flowing. Now, because it's negative, that means it's lost out to surroundings. Energy in transit, and it's going out into the surroundings. Okay, so you just got to be really strict with those signs before you put them into the equation, because the equation has a negative sign in it. And you want to be it to kind of like run true and be consistent. Okay, moving on to point J. For a solid, so if you've got a solid, and actually for most liquids or a liquid, okay, we say it's incompressible. So that means that the work done, so therefore the work done is equal to 0. If the work done is equal to 0, using the equation that we've got, just take the equation exactly as you see it, and then delta U equals Q minus 0. So therefore, all of the internal energy is given by either the heating supplied or the heating kind of like lost. All right, so that is what we have for solids or liquids. Just because it's incompressible, we can't do work on it because we can't change the volume. Okay, so the gain in internal energy is given by the heating supplied to the solid or liquid. Now that leads us on nicely to the last point, K. Lots of points in this section. Q, i.e. internal energy for a solid, is given by MC change in temperature. So Q is the heat supplied, but as we saw in J, that's also the same as the internal energy, is given by the mass, and let's have the mass in kilograms. That means change in temperature. We can have it in degrees centigrade here, because 1 degree centigrade is 1 Kelvin. All right, so that can be in degrees centigrade. You can have Kelvin there instead. And that leaves this little quantity here, specific heat capacity. Now, specific heat capacity, C, is given by, basically it says how much energy is needed to raise 1 kilogram of substance by 1 degree C. And you can see how that's come about because you've got the heat supplied here in joules. Okay, and if you divide it by the mass in kilograms and divide it by the change in temperature in degrees C, you can see that the units of specific heat capacity will be joule per degree C. So let's have kilograms first, -1, degree C, -1, like that. Okay, and so you can kind of like, that has come full circle in a sense. And the heat supplied, if you've got different substances with different, let's assume we've got the same mass, but for example, water and metal, they will have different specific heat capacities. The easiest one to visualize is if you've got a jam donut and you brought it out of the oven, and you know that the energy that the jam donut has had is the same whether it's the jam or whether it's the donut. It was the energy, they had the same amount of energy. But with a jam, because the specific heat capacity is much lower than that of the donut, it only goes up, it only needs a little bit of energy to go up by 1 degree, which means when you bite into it, you burn your mouth on the jam, not on the donut, because the temperature has risen greater for the jam and not the donut, even though it's got the same energy. All right, and it's all to do with specific heat capacities. So I think we have managed to get through all of those parts of the specification. We've addressed the idea that the internal energy of a system, i.e. U, is the sum of the potential energies and the kinetic energies. So we've done that nicely. The absolute zero is the temperature of system when it's got minimum internal energy. We had a look at that. C, the internal energy of an ideal monatomic gas, is given by U equals 3/2 nRT, and they've expressed that in terms of moles, but you can do it in terms of molecules or number of molecules. Part D, then, we're going into the terminology of thermodynamics there now. Idea that heat enters or leaves a system through its boundary or container wall, according to whether the system's temperature is lower or higher than that of the surroundings. We looked at the potato. So heat is energy in transit and not contained within that system. So we've had a look at that one. Okay, the idea for E, that if no heat flows between systems in contact, then they are said to be in thermal equilibrium, i.e. they're at the same temperature. Okay, so when a cup of tea cools down, eventually it will cool down until that temperature is exactly the same temperature as the surrounding. You go to have a drink from it and it doesn't taste as nice. Okay, because it's in thermal equilibrium with its surroundings. F, the idea that energy can enter or leave a system by means of work. So work is also energy in transit. So just like Q, that's the same with W. And hence, it's only delta U, it's only U that has a change in front of it. The Q and the W are energy in transit, so they don't have a change in front of them. Okay, the equation work done equals pressure times change in volume, used to calculate the work done by a gas under constant pressure. Okay, because the change is not in front of the P, it's only in front of the volume. But if P does change, then you can plot a pressure volume graph, and the work is given by the area underneath that graph. And then I, the first law of thermodynamics, the change in internal energy is Q, the heat supplied, minus the work done. And you've got to remember, is it by, is it on, is it, is it work done on the gas? Is it work done by the gas? Is it heat energy supplied to the gas? Is it heat passing out? So hopefully I've addressed that. And the idea that for solid or liquid, the work done is negligible, so that the heat supplied is the change in internal energy. So whatever energy you put in will result in a change of internal energy, i.e. the kinetic, if it was okay, all right, so we've done that. And then finally, to finish off, we've got Q equals mc delta theta, energy going into a solid to raise its temperature, and the specific heat capacity. So that is all for tonight's session, Unit 3.4 Thermal Physics. James, my colleague, will follow on from this, and he will do nuclear energy. And then we'll have a live session of taking you through a Unit 3 paper. And we will have done 4 topics out of the 6 for Unit 3. There's more from previous years online. So we look forward to seeing you at the live sessions to walk you through one exam paper. Okay, so I'm going to say good night on this and stop recording, and thank you very much for listening.